No, actually, for sure. All right, let's get started. So it is Halloween, so feel free to pass these around. I feel like I could get liability issues if I throw them, but I'll do is I'll just pass them down. Actually, we swapped the big one.
Yeah, of course.
All right, so this is the Trick or Treat Statistics lecture. So there will be a lot of trick or treat related lecture content here. So we'll get into that in a second. But just a reminder, we have this open lab sort of this week. So in place of the lab report is that input modeling report coming up. Then the next 2 weeks, we've got the output analyzer lab, which I still haven't made a video for. I ended up working on the homework video instead, but I'll see if I can do that today. But it's pretty self-explanatory. The slides are available. Yeah.
That lab report is due Sunday night, right?
That's right. It's like a normal lab report, but it just happens to be a final project. Then the next week's the lab 10, and then the next 2 weeks after that are open to work on your project as you like. Just reminders, the input model report's coming up. I've answered some questions about how much data you might expect to share or gather. So it's okay if you don't capture all of your data. Like if you say, wow, we picked a system that has kind of 8 things that we need input modeling, it makes more sense for you to go out and show me that you have the ability to capture like 2 of those and then tell me what the other 6 are. Question?
So
for the arena project.
Yeah.
So for those of you, there's like, I think 3 or so groups that are doing the Rockwell Arena Competition project. And this year they actually didn't give raw data so much as a more coarse outline of what things are. So if you're doing the arena competition, and there's only like three of you, or 9 of you, I guess, then you'll have to improvise a little bit. But I would say, tell me roughly what you view the inputs are that are from the data, and tell me what you know about them, and any details about how you're moving forward with your approach to solving your problem.
So it'll be mostly written, right?
So it'll be mostly, yeah.
Okay.
Just to clarify, the report does not need to be perfect, right?
No, in fact, it could be, this is just kind of a proposal, and your final work can be totally different.
So theoretically, at the end, if we notice that it's not going to work at all, can we just mention like preliminary conclusion that we're calling down to change our project? If you want us to just leave that?
I would say you don't even have to tell me that. If it doesn't work out, just go ahead and switch. We're not going to compare them.
Do a report as best we can.
Yes.
Is kind of sufficient.
Sir, right, yeah. I mean, the context is I recognize you just formed your teams, you just started thinking about this, and so I want to see that in the little time that you've had to pick out, you've picked a feasible looking system and you have the ability to move forward and be successful with it. So if this isn't the one you finally converge on, that's fine. We're not going to compare them, but we definitely need to at least see you're making progress so that you have a contingency plan to fall back on.
So it's not going to be harshly graded.
No, I would say that this is not going to be harshly graded. There are definitely ways to lose points on this, so do your due diligence. But if you do your due diligence, we're not going to say, oh, this is a crappy system or something. If you do pick a system that we think will be too challenging, we'll just give you that feedback. The feedback will come as comments, not as the actual grade.
Okay, cool, thank you.
All right, so detailed formats are online. I put like 4 sample input modeling reports. They're not ones that I've written. They're just ones I've randomly picked from students who got, I thought, halfway decent grades on them in past semesters. So hopefully those, you can actually see, not only use them for formatting, but see what did other students come up with and how do they navigate this. So hopefully that's helpful. There's these ICAs are available. Again, that one from last week. Due to the Canvas mishap, it's actually also still available and due the same time this one's due. I think, well, check the Canvas dates to be sure, but there should be 2 active right now, H and J1. And then G3 is up and available. You should now have everything you need to handle that. We'll actually go over the power analysis that is sort of more directly related to Lecture H, again, very briefly here in a couple of slides, and then there's only one more homework left. So, any other questions about the admin stuff going forward? All right, so now that all of you have, I think, decimated those bags, I would say happy Halloween, which actually, to protect the innocent, this was actually sent to me by one of you, but I will not reveal his or her name. But I appreciate the thought and I've incorporated it here. But it does allow me to ask, what is the sort of quintessential hypothesis test associated with Halloween? So that'll actually be our first attendance question. Just think about that. What would be sort of the hypothesis test, and I'll give a hint in a second, that you would associate with Halloween? So talk to your neighbors and see if you can figure. I'm a big pun in favor of puns, and so what do you think I be looking for? So, or yeah, what would be the well, I would say so. Or I guess I'd say is, what do people who go out for Halloween often say that kind of sounds like a hypothesis test? What's sort of the phrase we associate with when you get candy?
Oh, candy-based?
3 words with an or in the middle? So trick or treat, the classic null or alternative. So that's what I'm kind of looking for. So the attendance question I'm looking for here to show you here right now is trick or treat. This is the first one for today.
Oh, the first one for.
Yeah. So
I'm gonna submit again.
So happy Halloween. Quick review. We went over this in great detail last time, but hopefully you're feeling more comfortable with alpha and p-values. If it's helpful, you can think of alpha as a false positive rate. So I wore this Ghostbusters getup, and on the back of these uniforms, we see that they say down at the bottom, "We're ready to believe you." The bottom line here. Now, what that says is somebody calls you up and they say, "I've seen a ghost." Now, in reality, they just have observations. They've heard some rattling or whatever. And they then say, "Aha, that must be evidence of a ghost." Now, we as scientists would say, well, the null would be that it's just wind or something like that. It's not generated by a ghost. We have a null hypothesis that it's just going to be generated by natural processes. But what we're here to believe you, it says here, is that the alpha value of a Ghostbuster is much higher than the alpha value of all of the rest of you. They have a much higher false positive rate. They're willing to believe you. They're willing to say it's not the null, it's not the what you normally expect, it is the alternative being it's actually ghosts. Now, because they have a higher false positive rate, they also have a higher statistical power. So in other words, if it really is ghosts, they're going to find them. So that's sort of an interesting statement. When people say, when they're gullible, that just means that internally in their neurochemistry, they've adjusted their alpha values to be a little higher. And in some ways, that comes with a cost. But if you really need a Ghostbuster, who are you going to call? The one with the higher alpha value. And that will, because they'll also have the higher true positive rate, the higher statistical power. So stuff does, show up there. And this is the way I'm hoping with you're starting to start seeing the world. So there's a different ways we can use this terminology. So remember, I've been saying that we're saying positive means detecting a difference, and that corresponds to this terminology. So here's kind of the most difficult way to remember, what's type 1 error and what's type 2 error. This is jargon that is maybe not so easy for your customers to understand or your other stakeholders, but it at least is unambiguous. Because it sort of says, I know that I have a null hypothesis, and type 1 error means that I am going to reject it with some probability of the time, even when it's true. And so that's why we have this terminology. But it's going to be more common to talk with your colleagues using these terms like false positive and false negative. Now here we're saying that a positive value is detecting a difference from the null. So it's good to detect a difference, and so it's positive. Or you could view it as alternative hypothesis-centric, where it's positive because we've detected evidence for an alternative. So it's positive because if you view kind of it positive in finding the alternative. So that's one way to view things, but you have to be really careful because a lot of people who sort of aren't quite sure what you're focusing on, the alternative hypothesis or the null, will use the opposite terminology. So that this I'm claiming is the statistician's terminology, but when you communicate to your stakeholders, a lot of them will not know what you mean by false positive and false negative, and they might think you mean this, where you're actually referring to the null. So, in the case of if the null is that, well, actually the clanking that I heard wasn't ghosts, it was just wind that was going through the woods, just standard, your everyday, phenomena that is corporeal and real, and those sorts of things, you could say, well, if that's my null, then if I reject the null, then rejecting the null might be a negative, because you could say, well, maybe positive is in favor of the null. So I'm not saying that we should use this terminology here, but I'm saying it is a terminology that is used, and you have to be very careful when you use these terms negative and positive, being very clear what you mean. So that's why I will try to be unambiguous whenever I refer to these things, but in most of the lecture slides, see, me personally, I like alpha and beta, but the downside of that is when you're learning this stuff, I feel like it's really hard to sort of say, well, what is alpha again? So I like the terms false positive and true positive, true negative and false negative, where positive is a difference from the null. But if I use those terms, it's easy for them to get confused with this null-centric perspective. So I just want to sort of flag that as a potential problem and say that moving forward in these slides, we're using this common terminology, but just be careful you don't accidentally flip them and use this interpretation instead. All right. So graphically, this is sort of where this looks. And so if we think that this blue curve here is a distribution of things that could happen under the null. So if I hear clanking in the middle of in the backyard, then this is sort of the distribution of the types of noises I could hear out of the backyard through normal Arizona winds and other sorts of things that could happen in a backyard that would generate these types of noises. Now, one particular alternative for a hypothesis for those noises is that they're generated by ghosts. Maybe another alternative hypothesis is that they're generated by burglars, or they're generated by coyotes, or something along those lines. And each one of these would sort of have a different spot here. And in order for us to actually capture this true positive information, I need to know information about the alternatives. And that's where we'll get into next time, the sort of parametric tests and where that term comes from. But the idea is I assume the null is true, and that's the blue one here, and then I create some threshold for evidence, and I say that anything that is beyond that threshold, I'm going to say is not the null. And I accept that there is going to be a certain fraction of my null that will be beyond that threshold. And that difference that I detect, that positive result, will be a false positive. And so the false positive rate is equivalent to our alpha. Alpha is this area of the curve under the null to the right of our threshold. And so we would like to detect things in this curve. And so if we do make decisions based on this threshold, the area underneath the alternative is the true positive rate, and that's our statistical power. And so if we were to plot these two things against each other, false positive on one axis, true positive on the other axis, then we get a curve that looks like this one. And this is a so-called ROC curve, or Receiver Operating Characteristic Curve. Receiver comes from the point where back before we actually formalized statistical methods, there were radar receivers that had to make decisions on whether they saw like a submarine or whether it was just, a beluga whale or something like that. And how well they did at detecting the submarines got scored on a plot that looked like this. And so this was a score for how well the radar receivers detected, subs versus biological things. And so we've now more generalized this to talk about any sort of test where we've got two answers. So as you can see, if I move this threshold farther and farther this way, what I'm doing is I am making my alpha, my false positive rate, lower and lower. And in doing so, I'm also making my true positive rate lower and lower. And that's like moving this way on the curve. So as my alpha gets lower, my true positive rate gets lower. But if I go the other way, where if I move my threshold this way, then eventually I end up getting a true positive rate of 100. But I'm only getting a true positive rate of 100 because I'm saying everything is non-null. And so if I move the other direction, that's like me moving this way on the curve. And then I end up getting 100% false positives, but the upside of that is 100% true positives. So there is a trade-off between these two that I think is really nicely captured by this curve. Yeah.
So, if grouping of squares with false positive and false negative, is that similar to like a confusion matrix actually?
Yes, so if you're familiar with this term from statistics called a confusion matrix, so a confusion matrix, if you've taken, again, any a little more advanced statistics or even like an upper level, like even undergrad level machine learning class, you may have learned about a confusion matrix where basically you have on one side of the matrix, you have sort of what's true in reality, and then on the other side, you've got what you've ended up making a decision for. So you've got some data that was generated by ground truth, and then your question is how well did I actually classify that data into the two categories that it was from. So I had a voice, a bark from a dog or a bark from a coyote. And those are pretty easy to tell apart, but maybe there's some calls that are a little confusing in between. So I have a set of calls that are actually from dogs, a set of calls that are actually from coyotes, and then I test somebody on how well they can recognize the coyote or not, and then I can score them, and I will have their false positives, their true positives, their true negatives, and their false negatives. And the counts of these are the so-called confusion matrix. And another way that we can analyze confusion matrices or so-called contingency tables is with things like chi-square tests. So down the rabbit hole we can go. So this is just sort of putting a toe in the water of more sophisticated stats that will come if you move further on in this area. But for now, I'm just sort of focusing on this kind of nice ROC curve, which I think I often get questions, how do alpha and beta relate? And it's difficult to tell you exactly how they relate, but there is always this trade-off. And what the source of that trade-off is this geometric, what happens with this slice as you move it back and forth. All right. Any other questions about interpreting this? I'm sure you've seen images like this before. But in case you haven't seen them related to the ROC curve, I just wanted to show off that there is this trade-off, and the trade-off comes from the way these things overlap. All right. So, let's now drill down into seeing why the t-test works and why we have these funny assumptions about normality, for example, and independence. So the t-test, again, I gave kind of the history last time, was developed at Guinness to do some small sample statistics to improve the operations in their factories. A lot of these methods were developed with biologists working in agriculture, where they were doing a lot of large sample methods. But at that time, statistics is really run by biology, and biometry was a term that a lot of people used. How to measure biometry. And so a lot of this stuff got imported from agriculture into industrial, but when it got imported into this industrial space, the industrial engineers wanted to reduce costs, and so that's why they came up with these small sample methods that then bubbled back into biology, and then you got small sample methods in biology. So biology and industrial engineering have at least 100 years of going back and forth. And so it's interesting to me, I work with both biologists and industrial engineers now, that I think a lot of people forget that, and they don't realize that there was this tight overlap initially in developing these methods. So the idea here is we have this statistic. There is a hypothesis that some response variable y has an expectation that's equal to some mu that we specify. And so we are going to take samples of y. We are going to average them into y hat. And that becomes our one average. So this is our one sample. And so our hypothesis is here. We estimate the standard deviation, divide by square root of n, and we'll see why we do that in a second. And we end up forming this statistic, which gives us an idea of whether these samples could have come from a distribution with that mean. And so the idea here is if the data that go into the y here are independent and drawn from a normal, so that's important, with a hypothetical mean, mu, then this statistic will fall along a student t's distribution with n-1 degrees of freedom, and we'll see what that means here in a second. And so before we can do any of this, we really need to make sure that y are independent and normally distributed. Now the independence we usually get for free because we design an experiment where there is no way that our samples will communicate with each other. So you run your simulation and you use a different random number seed. And so by using different random number seeds, then the outputs of one simulation are going to be different than the outputs of another simulation. And so we can sort of just say a priori, these are independent. Or we design an experiment in the real world and we're pretty confident there's no way that these two things can interact in some way. So we usually get independence for free, but this normality, then we actually usually need to test for that. And so that's why I introduced things like the Shapiro-Wilks test, which is a test specifically for normality that has huge statistical power, like the Ghostbusters. And so the Shapiro-Wilks test, if it comes back not rejecting normality, you have a lot more confidence, even with very little data, that your data are normally distributed and you can move forward with a t-test. So where does this all come from? So the idea is that, well, under the null hypothesis, which is that our data come from a distribution with mean mu. So we're saying that under the null, which is like, in the backyard, we've got noises that can be generated from a normal. So this is sort of your conventional non-ghostly reality. And so on average, when you listen out to your backyard, you hear these noises, but occasionally you hear variations. And so there is a distribution of these things that we're calling Y. This distribution in our null hypothesis is that they're centered right on kind of conventional reality. And so we're going to take data, so we're going to listen to the backyard over and over again, and that will give us these data points. And most of them will be near the null if the null is true, but some of them will be over here. And then we are going to ask from those data, does it make sense that our null is true? And so we hope that all our data are normally distributed. So we do a Shapiro-Wilk on these samples, and it comes back and it says, yes, p-value is greater than 0.05. These are normally distributed. I do a QQ test, and it falls along the line. I feel very good. I've got the Shapiro-Wilk and the QQ test. Both look like they're normal. I can move forward. So these random variables, if I add them all up together and divide by n, that's my mean. And so the mean is also a random variable. And so the question is then, what are the statistics that correspond with this random variable, this sample? So this is a sample from an estimator of the mean. So I know that the mean of each individual sample from this distribution is mu under my null. And so then from the expected value of this sum will also be mu, because it's just mu plus mu plus mu all the way n times divided by n. And so that's what I get here, is that the expected value of the estimator is also mu. And so if I then just subtract off that, the expected value of this difference here is going to be equal to 0. So, all right, let's see where we're going with that. Now, what's the variance of this random variable? The variance of the estimator. And so I know the variance of each individual one of these. That's just the variance of my distribution here, my normal distribution. So this one's got some variance. Let's call it, we'll say it's standard deviation sigma, so its variance is sigma squared. And so with a little bit, if you remember from probability, from 380 and 385, if these are all independent, this is where the independence assumption comes into play, then the variance of this sum ends up being, you can actually end up combining the variances of the individuals. And so the variance, if you kind of walk through the kind of steps here, the variance of this estimator is just going to be n times the variance of each one of these. And so this n, since the constant, will end up coming out, and you end up getting that sigma squared. And in the end, after all of this, so then you end up finding the variance of the estimator is going to be just sigma squared divided by n. And so it's the variance of my distribution divided by n. So the distribution's variance, y, is distributed like a normal distribution with mean mu and variance this. And the estimator, I'm not going to comment on its distribution, but it also has mean mu, but it has variance divided by n. So as I increase my number of samples, then the variance of my estimator goes to 0. And that makes sense to us. So as we add more and more and take the arithmetic mean, we get more and more confident that our estimator will converge to the actual mean. And that's kind of where the t-test starts. So this observation is where Gossett went when he ended up building this t-statistic. So I'm going to simplify this variance divided by n, and I'm going to make it standard deviation divided by square root of n. And that term you'll see over and over and over again when we do confidence intervals, we do t-tests, we do lots of things. That is the so-called standard error of the mean. Whenever I say SEM, this is what I'm referring to. So when you hear people say error bars and standard error, they usually do not mean the standard deviation. They mean the standard deviation divided by square root of n. And the reason for that is they're not talking about the variance in the actual data distribution. They're talking about the variance in the estimator. So if I were to take these data over and over again and generate new estimates every time I take new data, that estimator moves around, but it moves around less than the actual data move around. And that's why we've got this divided by square root of n. And that comes from these calculations here. So this term we'll see again, over and over again for the rest of the semester. All right, so what can I do with that? Well, I said that under the null hypothesis, I've got this fact, and I've got this fact. And so by the central limit theorem, this estimator y bar, which is just a sum, will converge to a normal distribution that has this mean and this variance. And so that's all that I'm saying here, this mean, this standard deviation. And so I don't know quite what the distribution is whenever I don't have this limit, and I'll get into that in a second, but I do know that as the n goes to infinity, then my estimator will end up falling on a normal distribution centered on the actual mean of the population with a standard deviation that gets smaller and smaller with greater numbers of samples. And so I can subtract off that kind of on a step to standardization, and I end up saying that y bar minus mu is normally distributed with that standard deviation, but centered around 0. And then that is going to allow me to build my t-statistic. And so the t distribution is just this variable, which I said here is just normal with this standard deviation, standardized. So I'm going to divide by this standard deviation. And then if I do that, then I end up getting this standard score, which I know that as n goes to infinity, this thing is going to be a standard normal. It's going to just be 0 and 1. It's going to be a normal with mean 0 and variance 1 as n goes to infinity. Now for low n, it's not going to be normally distributed, but it's still going to look kind of normal-like. And that's where we get the t distribution. So with 1 degree of freedom, so that's when your sample size is 2, then you end up getting, so for reference, here's the blue curve as a standard normal, and the t distribution, notice it's got heavier tails than a normal, and it's a little shorter. And so this is my t distribution with 1 degree of freedom. Where does that degree of freedom come into play? It's because I have two, at this point here, I have 2 data points, y1 and y2, and I have calculated their mean. Y bar is just, y1 plus y2 over 2, and because I've fixed their mean, then I basically only get variation from one of them. Because once I know one, I immediately know the other because I fixed their mean. So what this is saying is that this t statistic that we've calculated here, given that I only have one variable to move around, then it can range along this red distribution. And so this will end up being that null hypothesis in that diagram that I showed with the two humps here. Now, as I increase my number of samples, the t-statistic tails go down and shrink in, and then in the middle, the mode raises up, so that as I add more and more samples, the t-distribution looks more and more like a standard normal. So a t-score turns into a z-score at high end. Was it the jacket?
No, the guy just locked in.
Yeah, that's what I mean.
For a while.
Well, that's what I mean. I wondered if it was the jacket scared him away. So, right. Yeah, there you go.
He was looking for an aggravation.
Yeah. That was the, yeah. So our t-distributions approach the normal, and so we'll often be able to actually approximate t-tests by z-tests, by normal tests, but this is sort of what's happening with that test over time. And so the idea here is we have this so-called pivotal quantity, t, which its shape doesn't change with, it only depends on the number of samples, on the degrees of freedom. And so for any hypothesis we give, so this was the null hypothesis we gave. It's normally distributed, it has this mean and this standard deviation. So for any hypothesis we give, because of the standardization in the t statistic, then we end up getting the same distribution here. And so every sample y bar corresponds to a point t along this distribution. So this distribution is effectively describing, I'll get to your question in a second, effectively describing your distribution of the estimator. So this is saying that if your estimator y bar, if we standardize it, then these are where those standardized scores are going to land. So as this is not describing the main distribution here. This is a rescaled version of the distribution of the estimator. And so a very rare t means that this estimator, this estimate that you got for y bar, is really, really unlikely for the hypothesis that you gave. And so the two-tailed p-value is just going to be the probability that the estimate that you found is outside of that threshold range. And so it's sort of here and out. And so an area underneath that ends up being what we use as our threshold for our alpha. And then the distance between these humps. And so if I look at the distance here between this t-distribution and a t-distribution under an alternative hypothesis, this distribution in big T space, that distance in big T space, will correspond to a smaller and smaller distance in real sample space as your n goes higher. And so in order to get more statistical power, what we're basically saying is that if I have the same difference that I'm looking for in the real space, as I increase my number of samples, this alternative hypothesis will move to the right. And as it moves to the right, then there'll be less and less overlap here. So what you're doing in sort of T space, when you're adding more samples, is you're dividing these alternative hypotheses from the null hypotheses. And in doing so, you are increasing your statistical power. So, so that's kind of where in the geometry comes back into play here. So more samples means more true positives. Less samples means more ambiguity and more of these, and so with more of these overlaps here, you get more of these false negatives. So that's kind of the mechanics behind how this t-test is working. It's just a standardized score of the distribution of the estimator. And under the null hypothesis, we know where the estimator should be. And then, based on the estimates we get out of the estimator, if they don't fall along the distribution where they should be, then we conclude that our null hypothesis must have been wrong. But we had to assume ahead of time that our data were normally distributed and that the sort of variance, we're not kind of worried about the variance, but we're effectively, if this were a two-sample t-test, we would also be assuming that the variance of the two samples were identical. And so we refer to this as a parametric test because the hypothesis really only lives in the parameter. It doesn't live in the distribution. We're hypothesizing only on the parameter. We're taking the distribution for granted. So that's the mechanics behind a t-test. Now there's a question back here.
Yeah. So basically what you were saying is that as we increase the number of samples, like the curve starts to shrink.
Well, it's not these curves. That's the beauty of this pivotal quantity, is that in the case of the t-test, the size of these curves actually stays the same. But as you increase the number of samples, it's true that the variance on the estimator's distribution shrinks. So you end up collapsing around a mean. But because this is a standard score, that collapsing around the mean actually corresponds to an expansion between the true hypothesis, which is like the true mean that's out there, and the mean that you're testing for, the null mean. And so as you increase your samples, the size of this red curve stays the same, but it just shifts to the right, at least for the one-sided t-test. For the two-sided t-test is a very similar interpretation. It's just easier for me to show for the one-sided. So any questions there about the mechanics behind the t-test? I'm not going to ask you to redo all of that, but my main point here is that in going through this, I wanted to motivate that I made use of the assumption of normality, and I made use of the assumption of independence. And so in order for me to make use of a t-test, I have to have both of those to begin with. If I don't, I have to turn to other tests. So let's go back to the Halloween theme here and to think about what we've just learned. So this is a guy named Neil Gilbert. He's a grad student. I think he's actually a biology grad student, not here. And so this was his clever Halloween costume once, where he's got this thing drawn here and the word student underneath it. And so, so then the question, is like, so what's the joke? So take 30 seconds and tell me why this is funny. So talk to your neighbors and chat about this joke. All right, let's bring it back in. So what's the joke? Why is this funny? Why is this supposed to be funny? So anybody? So for one, I made the comment, is this a normal student? What was I getting at with that pun there?
Because I don't know. It's because of the shape of the graph, and then the student is the t-test that we use.
Well, so if I remember, so if you go back and think about these curves here, then if I go back to the one with very low degrees of freedom, this is what Neil's drawn on his shirt, this fat-tailed distribution. This is not a normal distribution. This is a student's distribution. This is the student's t distribution. So what we see on Neil's shirt here is this, he's made these really large and made this a little shorter to say this is the student's t distribution. And so I would then come back and say, oh, you're not a normal student because it's not a normal, it's a student's t. And this is a student's t-shirt. And then so apparently Neil walks around all night carrying a bottle of Guinness because he knows the history of William Seeley Gossett at Guinness and a bunch of tea bags. So tea. So, this is a tea test. And so, so that's the joke here. Students' t-shirt. And I would say that, it's not a normal student. So a bunch of things wrapped up into there that you can feel free to make use of that. There's still time. to make this shirt. All right, so again, the big things I want you to take out of this is that a t distribution, in order to use it, you actually have to make the assumption your data are normally distributed, and you have to make also the assumption that your data come from that are independent. And if they aren't, well, we'll talk about that. But the big thing here is normality. And so you should do your Shapiro-Wilk test, and you should do your QQ plot, and both the Shapiro-Wilk test has a high statistical power, so that allows you to confirm that it's normal. And then after you've done that, so I'm not going to force you to do a Shapiro-Wilk in this class, but if you leave this class and you apply a t-test to a data set somebody's given you, then you can get into a lot of trouble if you say, yeah, I just ran a t-test. And they say, did you look at the residuals, et cetera, and you find out that, I shouldn't have applied a t-test. And so if you can't apply a t-test, so a t-test is what we call as a parametric test, because we get more power by assuming normality or assuming some distribution. If we can't assume some distribution, we lose power. But if we reject the hypothesis, it doesn't matter how much power we have. If we reject the hypothesis, it's still a good rejection, or it's still likely a good rejection. And so there are non-parametric analogs to all of the parametric tests that you've learned, say in 380 and 385. Question?
Wait, so if you assume normality incorrectly, but you still reject a null?
Well, so if I assume normality, and then if I assume normality and I shouldn't have,
Yes.
and apply a t-test, then I can't trust the result the t-test gives me. In other words, the alpha that I've been guaranteed on the t-test is not going to be right.
Okay.
And so I will end up having a different alpha that is just unknown. It depends on my distribution. But if I do want an alpha that I can trust, I can go to a non-parametric test. And so if you have a bunch of data that, now normally when you have a bunch of data that's not normally distributed, you can apply transformations. Like, it seems weird, but you can just apply the logarithm to it. And if you apply a logarithm to it, a lot of times the output will be normally distributed. And if you can detect the difference in the log transform data, it's still a difference, even though you transform the data. So it seems a little fishy, but it's legal to do. So there are ways to take non-normally distributed data and make them normal and apply your t-test. But if you can't apply the t-test, there is an analog called a u-test, TU. They're right next to each other in the alphabet. And so the Mann-Whitney u-test does the same thing the t-test does, but it kind of tests on medians instead of means. But it doesn't require any assumptions about your data, or basically no assumptions about your data going into it. So if you can reject the hypothesis with a u-test, then you're fine. You actually don't need to try to do any log transformations or whatever. But if you end up getting a negative result out of the u-test, you can't reject the hypothesis, then that doesn't mean you can accept the hypothesis. So maybe you should rethink getting more statistical power. And the way you can get statistical power might be to log transform your data or arcsine square root transform your data so that you can then use the t-test. And so other tests that you've learned about, the pair difference t-test, the non-parametric analog is the Wilcoxon sign rank test. The ANOVA, the non-parametric analog is the Kruskal-Wallis. So basically any conceptual models that you've built about statistics through these things, basically if you ever need a non-parametric version, if you just Google for non-parametric ANOVA, Kruskal-Wallis will come up. And so initially, that's how we all do it. We're just doing the equivalent of Googling for non-parametric versions of the things we learned in school. But initially, you'll end up getting this mapping, and you'll get a nice decision tree in your head. We'll be able to pop these things off like nothing. So work on your recall of these, but most of the class is going to be focused on these, but always with this assumption of normality. All right, so let's see an example. So this is like just out of your homework. So I'm going to do both the paired difference t-test and the power analysis in one, which is very much like the second problem of your homework. So the idea here is you build a simulation model, and it supposedly simulates the real world. You've got input data from the real world. You've got output data from the real world. And you would like to see, does your sim generate the same type of output data for the same type of input data? And if it does, then you're willing to say your sim is a good surrogate for the real world, and you can just experiment on the sim and not the real world. So I'm going to take my input data and feed it directly into my simulation instead of using random numbers. This is one approach we can do for this. And so each sequence of real data, input data, then I obviously have real output data associated with it. But then it also generates simulated output data that's associated with each input that I fed in. So now we've got one input, one set of input data. So one set of input data, sorry, Neil. And that input data naturally went into the real system to give us output data, but we are also going to artificially insert it into our simulation and produce simulated output data. And then our question is, are these two equivalent? And if they are, and if we have high statistical power, so if we have, if we have, a low beta, so if beta is low, I'll say beta low, or the statistical power high, then, and we conclude that these are equal, then we can come back and say that we have a good simulation that we can use. So, in order to capitalize on getting enough power out of this, so normally when I look at these things and I see two outputs, two data sets, I would apply a two-sample t-test. One sample here, one sample here. And so a two-sample t-test I might have a z hat and a y hat, and then my test statistic would be like y hat minus z hat over this standard deviation divided by square root of n. But the downside of a two-sample t-test is, for one, the power analysis is harder to do, and then two, it has less power than a one-sample t-test of the differences. And that's what we're going to do here. So what I'm going to do is, since every output in the real world has a corresponding output in the simulated world, I'm going to subtract these two and get a difference. And those differences are the real outputs that I am going to test. And so I want to see if the string of differences that I get out of here I'm going to test it against the hypothesis of a zero mean. And if I can show that the differences of a zero mean, then I can conclude that these two outputs are equivalent, at least in the mean. So the power analysis is also very easy for me to do for this one-sample test. So I'm converting a two-sample test into a one-sample test, and the only reason I can do that is because the outputs are paired. If these outputs were generated with a different input stream than this one, then it's like I don't know which ones to subtract, because I could, sort these one way and sort these another way, and then I would come up with artificial pairings. But there are natural pairings here because the sim and the real world both have the same input data going into them. So and this is what we mean by pairing and statistical blocking. We are blocking the outputs based on this single input. So we create input blocks, and that actually increases our statistical power, which is what we're looking for. So we've got our real outputs, we've got our simulation outputs. We're going to not do the two-sample t-test, and instead we're going to take differences of all of those, and we get a single vector of differences. So you'll calculate something like this on your homework. And that single vector of differences, I can calculate a mean difference, and I can calculate a variance. And so I've got this mean and variance, and now this mean and variance I can then use in a normal one-sample t-test. And that is all a paired t-test does. So if you go into your stats package and you give it two vectors and say do a paired t-test, internally it's going to take these differences and then do a one sample. And that's all you're doing manually. And so if the hypothesis is true, then these differences should have a distribution of with a mean of 0. If the hypothesis is false, then the mean should be far away from 0. So my t-statistic is down here. It's just my mean minus my hypothesis. My hypothesis is 0 divided by the standard deviation over the square root of samples. And so because the hypothesis is 0, it just becomes this thing. So this is my t-statistic. It's just the average of this column divided by the standard deviation of this column divided by the square root of samples, where the samples are the number of rows in the table. So that is my t-statistic for this, and I can then do a normal t-test, a one-sample, two-sided, one-sample t-test. Now, what about power? I said that I need, in order for me to conclude that the simulation is close enough to the real system to use, I need to guarantee I have enough statistical power. So I say, well, okay, what's your false positive rate? It's 0.05, that's kind of conventional. Then I ask, what's the desired true positive rate? That's another name for statistical power. And the boss comes back to me and they say 80%. We want you to, the true positive rate, the area on the right-hand side, of that red area on that alternative hypothesis, we want that to reflect an 80% rate. So that's the true positive rate there. And then we have to ask, okay, and then what's the smallest difference that you're willing to tolerate? Like, I know I'm not a perfect simulation modeler. My sim is not going to be a perfect match for the real world. How close do I have to get for you not to care about the difference? And they give you a number, capital D. And that capital D might be like, oh, it's one performance unit. It's one person in a queue length or whatever. And if my sim is different by less than that, we're okay with that. If my sim is different by more than that, the sim is bad. And so I need to be able to detect differences that are that big or more. So I then convert this, I use the standard deviation of the differences along with this minimum detectable difference, and I scale that to create the effect size, delta. And that effect size, again, it's just a scaled version of this mean D. And I get that just by the standard deviation of this column, and I just scale the delta by that. So now I'm basically saying, how many standard deviations away are you allowing my sim to be? That's all this effect size is. And this comes back, and let's say it's 0.5. That means that whatever data you get out of this, and this is under the assumption that the variance between this and the real world is true, or is the same. So we're kind of, that assumption might be, there is something called a Levene's test where we can actually test to see if that's true. But if we take it for granted that this variance is a good estimate of the real world variance, then this is saying that as long as we are less than, say, 0.5 standard deviations away from the system mean, then we're okay with that. So we calculated this and we're given these things, and that's when we turned our operating characteristic curves, or OC curves. You can find in the back of the book. And you can find them, and they're specified for several different true positive rates, or alphas. And we're going to pick the one for 0.05. And then that lets us zoom in, and we see that we've got effect size on one axis, and we've got beta, which is our, if alpha is our false positive rate, then beta is our false negative rate, which is 1 minus statistical power. Question?
Going back real quick to the other equation, could you repeat what D, like capital D was?
Capital D is we're saying that the mean simulation output must be no more than D away from the mean system output. So it is our tolerance on how close our simulation has to be in performance to the real world.
Okay, and is that like given?
That would be given to you by the application.
Okay.
So you really, if you're measuring queue lengths, or if you're measuring the number of people waiting in a queue, if there's on average like 30 people waiting in a queue, and your sim says, oh, well, actually there's 29, you'd say, well, 29 and 30, it's not that different. So 1 person difference I don't care about. I'm okay with your simulation.
And S is just regular standard deviation, right?
And S is the estimated standard deviation from these data. Big S is always sample standard deviation. All right, so then I've got my operating characteristic curve. This here, as I've put the little reminder up here, is just statistical power is just 1 minus beta. I specified the statistical power was 80%. So that means beta is 20%. And so the idea here is I'm going to focus only on this 20% line across here. And so basically I say, all right, across this 20% line, I now look, and I was given an effect size. And so I took that D, that capital D, divided by the standard deviation, and that gave me an effect size. And so then I find wherever that effect size was, let's say it was 0.5. So then 0.5 is this line here. And so this line intersects this line at this particular point, which happens to fall on the operating characteristic curve for 30 samples. So that means that I need 30 samples to do the job. Questions?
So is there a relationship between just regular OC curves and the ROC?
Absolutely. So you can kind of think of so as in an ROC curve that I showed before, if you've got your ROC curve, which effectively is plotting alpha on this axis, and so alpha is our false positive rate, and then statistical power is our true positive rate, and there's this diagonal line, which is kind of your worst case, and you've got these curves, and for one statistical test, if you increase the number of samples, these curves get more and more kind of corner-like. And so you could imagine writing like n equals 10, n equals 20, n equals 30, and doing a similar analysis with these curves. So this is just plotted in a different way, but it's all the same data. Okay. So just as a recap, we said we wanted 80% power, which is 20% false negatives, 20% type 2 error. We said we wanted an effect size of 0.5, so that's here. Those intersect on the curve that happens to be 30 samples. And so that tells me that if I have 30 samples, I can do the detection task. My test is sensitive enough to detect the desired difference between the simulation and the reality. If I add to my number of samples, so if I go down, then that is going to move on curves that get closer and closer to the origin. And those curves, as they get closer and closer to the origin, that's basically saying for the same statistical power, I can detect smaller differences, or for the same difference, I get more statistical power. And so that's what's being represented by these curves that are shaped this way. And so both of those things together are kind of like what you're going to do in part 2 of that homework. So are there questions about the process here? And fortunately, there are now in MATLAB and R, there are tools that do all of this for you. If you know, they're kind of, you basically give them the variance you want, the desired effect size, the type of test, and you either give them the number of samples or the statistical power, and they give you whatever one you don't give them. And so that is effectively them implementing the OC curves internally. But they're only defined for a small set of tests, like a z-test, a t-test, a chi-squared test for variance. There's a couple others, because it's really hard to do a power analysis analytically, because you never know what your alternative is. That's why in the parametric test, you at least have some guess at what the alternatives might look like. If you want to do a power analysis on more sophisticated tests, you have to use these Monte Carlo methods. And so there are much more exotic tools you can buy. And if you work in an industrial statistics shop or maybe finance, then they'll have those tools. And you'll buy those software packages, and they will end up doing all the complicated power analysis and be able to tell you, what this graph is telling you, but for a complicated test. All right. So any questions about that? All right, so let's do then a quick background then on where the hell does this 5 sample constraint come from in the chi-squared. So chi-squared is the other test that we're going to be using. And so this is our chi-squared statistic here. This is it's simplified for 2 bins. And so it's sort of a funny formula because it's squared in the numerator but not in the denominator. It looks like the units don't match up. So it's a weird test. It looks very arbitrary. So where does it come from? And so the idea is, well, imagine in the binary case, you basically have two bins. Or you can think of it as like I either landed in the bin or I landed out of the bin. So every bin becomes kind of like just like a coin flip. Did you happen to land in the lucky spot or the unlucky spot? And so in that case, I might view it as a binomial test. And so a binomial test, it just has 2 outcomes. And I say for n number of tries with this probability of landing in the bin, then what are the distribution of things that land in the bin or out of the bin? And what we find is that as the number of samples times the probability gets large, the binomial distribution, even though it's discrete, approaches the normal distribution with where it has a mean of n times p and a variance of np times 1 over p, or 1 minus p. And so this, if I assume that I have enough samples, then this binomial, if I were to create this chi variable, and I just define a chi variable, just call it chi, and it's just going to be the number of observed successes, the number of things that land in the bin, minus the expected number that land in the bin, divided by the square root from this distribution here. And so chi is just the standard score of how many things land in the bin. And so this chi is, since I've standardized a normal, then I get a standard normal out. And so chi is distributed like a normal with 0, 1, with 0 mean and 1 variance. So a simple z-test would suffice instead of a chi-squared test if I only had 2 bins. Question?
Yeah, you said the little triangle right there means just approximation.
Oh, sorry, triangle means defined.
Okay.
So this is equal by definition. I just called it that. It's like a name. All right, so now conveniently, if I do a partial fraction expansion, so you might remember from, I don't know, analysis or something like that, I can take this thing and expand it into 2 fractions. And what I end up getting is actually the chi-squared test back out. So if I square so all I'm doing is I'm squaring this to get rid of the square root, and that puts the square up there and takes away the square there. And then after I've squared it, I do an expansion, and then I get these 2 components. And if you look at it, the blue portion, this is the number that I observed in the bin. This is the number I observed out of the bin. This is the number I expected in the bin. This is the number I expected out of the bin. And they were both divided by their expectation. So that is the chi-squared. So 1 squared normal gives me contributions from 2 bins. So, I can end up, there's my chi-squared right there. 1 squared normal gives me contributions from 2 bins. 1 degree of freedom, so once I know how many are in the bin, I immediately know how many are out of the bin, gives me contributions from 2 bins. And then that finally lands to k minus 1 degrees of freedom gives me contributions from k bins, or k minus 1 squared normals describes contributions from k bins. And so that's where the chi-squared test comes from, is it's this realization that we're just approximating this binomial distribution of how many things land in a bin or out of a bin by a normal. And once we've got that, then this just follows from that approximation. So this is a so-called continuity approximation. So in our chi-squared test, these scaled squared differences from each one of your bins are actually distributed as the sum of k minus 1 standard normals. So where do you get a chi-squared distribution? It is the distribution of, if you added up, k minus 1 standard normals that were independent from each other. And that's where you get this funny distribution that we talk about. And so in order for us to make this assumption of this continuity approximation, we need our expected value to be 5 or greater. That's equivalent to saying we need NP, the way I started here, we need NP to be large. So I think somewhere here I said, NP sufficiently large, I can make this approximation. That's equivalent to saying that with the expected number in each bin to be greater than 5, I can make that approximation. So that's where that comes from. And here's what chi-squareds look like. So they initially look kind of like a Weibull, and then this green one with 2 degrees of freedom is actually an exponential. It is an exponential, and then they get more hump-shaped, and that should make sense because they're describing a sum, and things that sum by the central limit theorem naturally converge to the norm. And so that's what you're seeing right here in the chi-squared. So that's where that assumption comes from. So if you have too few samples, your binomial won't be approximated by a normal, and none of this math will work. So that's why I'm a stickler on it's got to have at least 5 in the bin. All right, so questions about that before we wrap up with a couple of very minor comments about sim? All right, so we had this example before with the bank. You did a little model. Let's say you you did, this is like, say, for your final project, you have a model where you've got input variables, decision variables, and these outputs. Now, for your input variables, the statistics you're going to need are statistics that help us test for goodness of fit. So there's statistics that have a premium on statistical power because we actually don't want to reject a distribution. We want to accept a distribution. But you can only accept a distribution if your test has high power. So that's why, like, Shapiro-Wilks is used if you're looking for normal. For the rest of these, Anderson-Darling is a little bit better, but it's just something that, I'm going to say that, looking at high p-values is not necessarily going to be a useful heuristic unless you can back that up with saying I have a lot of data. So I'm not going to force you guys to do fancy power analyses, but I at least want you to say my high p-value is validated because I have a lot of data. Now, let's say we now shift and we're focusing on the output here. If we have one output we're looking at, so that's one dependent variable, one so-called response variable, you guys already know the stats that you can use for that. These are your stats you're familiar with: t-tests, ANOVAs, linear regressions. Now, the problem comes into play is that our sims are going to have multiple outputs. And so we might want to compare a simulation of the standard, the status quo, with a simulation that we think is better. And now we've got 3 different ways to compare the 2 simulations. Are they better in terms of teller utilization? Are they better in terms of average delay? Are they better in terms of maximum line length? And if you find that one of them's better and the other ones aren't, you might get into this ugly fishing problem, and that's what I'm saying, what could go wrong? And I'll just sort of cut to some of the chase here, just for time here. But the idea here is if I ran a t-test independently on these 3 things, and these 2 t-tests don't reject or don't show a difference, but this t-test does, it may not be legal for me to say that one sim is better than the other. Because if you remember, each t-test has a false positive rate of 5%. And so if I think about it, 5% of the time I'm going to see a difference here that doesn't actually exist. So if I do a bunch of these things, and then overall, because one of them is different, I come back and say my simulation is better, I might have just accidentally found a difference when my simulation isn't better. So how do I deal with that? Fortunately, we have ways to deal with that. So when you find yourself comparing multiple tests, or using tests multiple times to compare the same 2 models, then we do what's called the Bonferroni correction. And what we're doing here is this is me just saying mathematically what I said before, where if every test has an alpha, a given alpha, then the family level alpha is going to be greater than that alpha because you fish for differences. But if I then convert all of my individual tests to have my desired alpha divided by the number of comparisons, then my family level alpha will go back to what I expect. So I won't inflate my type 1 error. And so when you're doing these multiple comparisons, you got 2 simulation models with multiple outputs, and I'm doing a t-test on every single output. Before I can do that t-test, I need to then adjust each individual t-test alpha to be my desired alpha divided by the number of comparisons, and then you're okay. Now, this one here is kind of an ugly, this is kind of a coarse, this is a brute force way to do it. A little more precise way to do it is to use something called a Manova, or a multivariate ANOVA. And that can do it in one shot and has much better power than this one here. And then you can also do an ANOVA with a post hoc test, and there's all sorts of these post hoc tests. But all of this stuff that has been invented to deal with exactly this problem. So this is a real problem that's out there. For now, I'll say the Bonferroni correction is the easy thing to do, but if you happen to have access to statistical tools that you see these words pop up, Tukey test, Fisher's LSD, Manova, this is the preferred way to do it. But if you, in a pinch, this is not a bad way. All right, so that's all I've got. So are there any questions on that? Did all of the candy get distributed? That's fine. My grad students don't need any more. All right, so in that case, let's finish with the last attendance question here. And so my question is, not reaching that far back in your memory, if I need to do k-t tests to decide if I want a false positive rate of alpha, and I need to use k-t tests in parallel to look for differences across multiple variables, then what false positive rate should I configure each t-test with? So I want a false positive rate for all of the comparisons together. So I want to do k-tests that together have a false positive rate of alpha. So then what false positive rate do I use for each test? Otherwise, the alpha that I'll use, if I use alpha for the t-test here, then my false positive rate for the family will be much, much bigger than alpha. So this is what I was just talking about, just seeing how many, what your recall is at the end of the day. And otherwise, that's all I got for you, so I'll see you next week.
Yes, it is interesting. The email you were talking about.
Yes.
So, is there a way to prevent